Okay, today we're going to do the labs for Chapter 6, linear models and regularization methods. And we'll start off doing forward stepwise selection. But as always, the first thing we do is we import the libraries that we need for the lab. And you'll be familiar with this by now. There's one little extra thing here. There's a library we're not actually going to use in this lab, but notice this exclamation pip install. We install in a package on the fly here, and you see some printout that follows it. And so you can do that. If you don't have a package installed, you can just, in the Jupyter Notebook, install it on the fly. So we did that just to demonstrate it. Yeah. But we're going to go to forward stepwise selection, and we're going to run forward stepwise on the hitters data using celery as the response. Okay. Now, there's a little problem here because in the hitters data, there's 59 rows that have missing values for celery. Now, when you do regression, if you have missing values in some of the predictors or features, you can do things about that. You can maybe put the mean value in, or you can have ways of imputing. But if you've got missing values in the response, you can't do anything. So you just get rid of them. So we use the drop NA method to get rid of the missing values in that data hitters frame, and now we're ready to go. And of course, that reduces the size of the data set by 59, because there were 59 that were there. So in the chapter, you learned about using CP statistic to do model selection. And CP is quite a well-known statistic. And so we're going to do that here. But the problem is it's not built into...
it's not in sklearn.
It's not in sklearn.
Yeah, so here we're going to show you how, if you have a metric that a custom metric that you like, you can define a metric, using this kind of signature and use the same cross-validation methods to tune with that metric. Yeah. Here we use CP, but you might have your own for whatever purposes.
And that's a great feature because that empowers you. If you've got your favorite metric, you can do it. So here we write the function, and you can go through the details. You see the definition of CP in the chapter, and you'll see that's what we do in there. One little catch is that sklearn tries to maximize a score, and so we want to actually minimize CP. So the function we write is the negative of the CP statistic.
Yes.
So that'll work out. Now CP also requires in the definition an estimate of the residual variance, sigma squared. So what we're going to do there, and that's what's in this code here, is we just fit a model to all the data and estimate sigma squared once and for all, and use that estimate of sigma squared using all the variables. Okay, and that's standard practice.
When using CP.
Using CP.
Yeah, and one little thing I'll just note, if we go and look up at the signature of NCP, and maybe I can take the pencil for a second. The first argument is the sigma squared, which we have to set, but the metric, it should have a signature that takes an estimator, an X and a Y, so we want to fix this argument. And that's what this line here does. It takes our original estimator and fixes the value of sigma squared in it.
Okay, so now we're ready to go. Our neg-CP function can be used to do the model selection. So next thing, we set up a strategy for how we're going to fit the sequence of models. Okay, and so that's this chunk over here. It defines strategy as stepwise, which is forward stepwise, first peak. So that means it's going to run forward stepwise until it reaches the peak, until in this case it's going to be the CP statistic, negative CP starts decreasing, then it's going to stop there. So that's where it's going to stop, rather than going through the whole function. Although in this case, actually, we do use all the terms. Right?
Yes, yeah. So actually, in this one, if you look, we actually haven't put in a score, so we're actually not using the negative CP. It actually, by default, is going to use something like R squared or training MSE. In the next example, we'll have the neg CP. Yes.
So in fact, we're not using first peak.
Well, we are using first peak, but not neg CP. So we will just use training sum of squares. So if you allow it to go to the end, it'll include all the variables.
Okay. All right. So now set up our method, and it's going to be using sklearn selected on using OLS as the fit-in method with the strategy that we've just defined. Okay, and now we run it. hitters._msc.fit. That's the function. We use the fit method using the hitters data and the response y, and we can extract the selected state, which is the selected model. And what we get in this case is all the variables, because we didn't tell it to use CP to select, so it just selected the whole lot.
You use training MSC as the score. Yeah.
Is that the default?
That's the default, or it's either that or R squared, which will be one-to-one functions of each other.
Because here we didn't specify a selection strategy, whereas next time we use it, we say scoring is neg CP.
Yes. Yeah.
So if you don't select, it's just going to fit them all. So when we do the fit using the scoring method over here, the steps are the same as before. What you see is a smaller subset of the features that were selected. Okay, so that's selecting the model by CP. Mm-hmm. I think the next method that we're going to use, the same forward stepwise, but we're going to use the validation set, in fact cross-validation, to select the model. Okay, which is probably a more general method and can be used for any kind of modeling. So here the strategy is stepwise fixed steps, because what we're going to do is always use a full set of steps, right? And we're going to score every single step. Mm-hmm. And you'll see we're going to make a plot afterwards that shows the performance as a function of the step size.
That's right.
And again, the full path we define as using the OLS method along with the strategy over here. And let's fit the full path on the hitters data. And so we do that, and so that will fit a sequence of models, and we also get we call it the y hat n. We get predictions on the full path. We give it the hitters data, and it gives us back a matrix of predictions. Right?
So, and what are the columns of that matrix? I guess they're the different fitted values as the model grows.
Yeah.
Yes.
That's right.
Okay.
So there's going to be 20 terms in the model. The null, that includes the null model and the 19 features added in importance one at a time. Importance in terms of residual sum of squares, right? Because this is not using any scoring method.
That's right.
Okay. So we want to make plots to show how these mean squared error and other measures, how they decline as a function of, or change as a function of number of steps. So we've written some code here for doing that, and the code sets the size of the plot and sets the labels and so on, and we'll make the plot for our first sequence of models, which is just using mean squared error.
And this is just evaluated just on the training data itself.
Yeah.
Subsequently, we're going to look at cross-validation and the validation set method and add and compare them to just using the training data.
And you'll see, if you look at the code we knew what sort of range we needed, because you can see this range is a bit bigger than we need to plot this curve, but we were anticipating what we were going to see later on so that they could all fit into the plot.
Yes.
Now, the other thing to note, and of course this has to be the case, is that the residual sum of squares is decreasing at every step. Because as you add more variables, you can only do better in terms of mean squared error and residual sum of squares. Okay. There's some details about how we compute the residual sum of squares, and we explain some of them in the text here, but we won't go over that now. Okay, now we're going to use k-fold, in fact 5-fold cross-validation, and we're going to use the sklearn cross-validation technology that we've already learnt in lab for chapter 5.
Yeah. Though, Trevor, I think there's actually something new in this. So we're using this function, if you look at it, instead of called cross-validate, which we saw, this one's called cross-val predict. So what that gives us is actually the predictions for whatever for the whatever the method is, and the cross-validation. It'll give us the predicted value. So on each fold, you'll get the predictions having trained on the remaining folds.
Okay, so that's a function in sklearn?
Yes, yeah. And so that's why the y hat CV has the same shape. It's actually all 20 cross-validated predictions.
Ah. Okay, so that's really convenient, because sometimes you want these prediction matrices that have been predicted in an honest way through cross-validation, and you can compute any measures you like. And in this case, we are going to compute mean squared error. Okay. So in this chunk of code here, what we do is actually compute the mean squared error. This cross-validated prediction matrix has got 20 columns again, and we want to compute the mean squared error for each of those columns, but this will be cross-validated mean squared error. Yes. Right? So in doing so, what we do it in 2 steps. We compute this matrix here, which is 20 by 5, and that's the cross-validate, the average error inside each of the 5 folds. Okay? And so there's 20 different models. There's 5 folds for each. We get a mean squared error for each. So why do we do this? We could have just computed the average over everything. Well, we want to also compute the standard error. And so our final estimate of mean squared error is going to be an average of these 5 numbers, and then we can have a crude estimate of standard error for the average. Mm-hmm. So that's why we do that. Okay?
Yes.
And now, having done all the work, we now add the cross-validation estimate to the mean squared error plot, and this is the code for doing that. And there we see the results.
Okay.
And so
it seems to flatten out a little bit. It doesn't necessarily have to drop, of course, like the in-sample one, but it seems to flatten out some.
And you sometimes see that, and of course you have to take the standard errors into account.
Yes, yeah.
But if I were to look at this plot, Jonathan, I would say maybe a model with 6 terms is a good model to select.
Yeah, that looks promising. Yeah.
And the standard errors help us make the selection. Okay. We're also going to add to the plot. We talked in the chapter about the validation approach, where in the validation approach you just set aside a training set and leave some data as a test set. And so here we give code for doing that.
Yeah. So I guess for this one we won't get the same standard errors we did for
Yeah.
cross-validation. Right? Oh,
okay. We get no standard errors.
Yeah.
In fact, so the code looks pretty much the same, and this is the error on the validation set that we get when you just have one validation set. Mm-hmm. Now the interesting thing is this validation set was randomly selected 20% of the data. Now in the 5-fold cross-validation, they were also 20%. The validation sets for each fold was 20% of the data. Mm-hmm. So this guy seems a poor estimator compared to the cross-validation, because you only get the benefit of one curve, whereas cross-validation, you do this 5 times, you get to average the curve and get a better
it should be more stable, I would guess, and averages out the errors.
And you get the standard error.
Yes. Okay,
so that's it. We're going to skip the best subset selection, and the next section we're going to discuss is going to be ridge regression and lasso.